Hello, and welcome to this lesson on solving optimization problems. Optimization problems are problems where you are trying to find the largest possible or smallest possible um, values of a function or some criteria, usually some physical criteria. We're also going to review just how do we find the absolute minimum and maximum of a function in general. So when we talk about optimization problems, we usually mean like a word problem. And in the word problem, what you have to do is come up with the function first. I'm going to do an example of what you do with when you already have a function first. But so when you have a word problem, it's always helpful to define the variables and draw a picture. And we'll see that. And then for the objective function, that's what we need to, we also need to know what it is we're maximizing or minimizing. Is it area? Is it length? Is it volume? So we're going to sometimes have two equations when we have a word problem. And then we're going to work with those two equations so that the equation we're trying to maximize or minimize, the area, say, as we'll see in the first example, is only written in terms of one variable. So sometimes you have information about two things and what they add up to. And then the equation you're trying to maximize uses both of those things differently, and you have to get it down to one variable, though. So you'll see that more clearly in the example. And then we need to understand the domain. Like, if you only have 100 feet of fence, you can't get an answer that's bigger than 100. And you can't get negative values. And then we're going to use calculus to find the maximum or minimum on the interval of interest. And we have to, as always, if we're looking for an absolute maximum or minimum, we have to check the endpoints. Often in these problems, the endpoints are trivial, like it gives you an area of 0, and that's what you're trying to maximize. But there are cases where the endpoints actually give you the most, making one thing the most it can be or the least it can be, gives you an optimization of the value you're looking for. So let's move on here. I didn't mean to write there. Let's just review finding the absolute minimum and maximum. Now, you've been working with finding minimums and maximums a bit. We did the first derivative test, the second derivative test. But when we talk about absolute minimum and maximum values, we have to use those techniques where we check critical values, but we have to add two other function points as possibilities, and those are the endpoints. When you're asked for an absolute minimum or maximum, there's an interval that's either implied in the word problem or, as it is here, stated. So we start with our techniques for finding minimums and maximums of a function dealing with the critical values. So the first thing you do, you have a function, and you know that functions that kind of go like this maybe, and this is a polynomial, so I can go like this. When I'm down here, I'm at a bottom. When I'm up here, I'm at a top. What those have in common is that first derivative is 0. So you find the first derivative. (6x squared minus 8x minus 1). And then you solve to find the critical values. Now, there's no critical values occur in two ways. One is at zeros of the first derivative, and the other is at values where the first derivative does not exist. This first derivative is a quadratic, and there is no x value that's excluded from its domain, so we just need to look for the zeros. So you do that. You can use the quadratic formula. This does not factor easily, or you can use your calculator and solve it using the graphing tools, either by finding the intersection or by doing the calculate 0. Do not use the trace key and get an approximation. You want to be right to at least the third decimal point. So use one of those tools. There are videos available in Blackboard for that, or you can email me for help. But the quadratic formula works fine for this one, even though it can't be factored. And what you do is you get two answers, negative 0.115 and 1.448. So these are my critical values. Now, I need to know which is a max and which is a min. And you did this in a prior unit. You made a little sign chart. You put your critical values in order on this number line. That's a 1.448. And then you checked the sign. Well, a number, if I test -1, if I find f of -1, I'm going to find out that I get a positive value. 0 is in between these two numbers. F of 0 is a negative value. And I could find f of 2, and what I see is I get a positive value. So because this goes from, the derivative is positive, so the function is increasing to the function is decreasing, and the function is decreasing and increasing. This is a local maximum, and this is a local minimum. So you know those are local maximums or minimums, but on this interval, from -1 to 2, are those actually the highest? Well, these values of x here, these critical values, create the highest and lowest values of x in the entire interval. You don't know that until you also check the endpoints. So what you do next is you just make a little table of values. And you can use your calculator to calculate these values. But what you're going to do is take what you've done when you found the critical values is found numbers for x that you have to check to see if that y is the highest or lowest in the interval. So there's x and f of x. Let me make that look nicer. Okay, hang on. All right, there we go. So I'll make an x. I'm starting to write sideways there. So I need to check the y coordinates of all of the critical values and the endpoints. Well, the left end was -1, and I don't have to do this in order, but I tend to do that. So I've got the two critical values here, and I've got the endpoint. Now, notice I'm checking the function value because I'm interested in the maximum of the function. The derivative tells me where to look, but I don't want the maximum of the derivative. I want the maximum minimum of the function. So when I put these into the original function, which when we look up here, the original function was 2x cubed minus 4x squared minus x plus 2. When I put these function values in, when I put x into this function, I get -3 when x is -1, 2.059 when x is -0.115, and I tend to do these in a table, but you don't have to in the calculator. -1.763 is y when x is 1.448, and when x is 2, y is 0. So now I look for the highest and the lowest y in this list. So what I'm going to see, let's see, the lowest y appears to be, I have negative numbers, so the lowest will be the most negative. That's the lowest value. That is my absolute min. Absolute minimum. That's, if you graph this, you will see that is minimum. I don't think I'm spelling that right. If you graph this, you will see that at x equals -1, you get y equals -3, and that's the lowest point you'll see in the graph if you only look from -1 to 2. And then I look for the highest value. Well, it's not negative. I got a 2.059. There is no positive number for y higher than 2. So this here is my absolute maximum. So the answer to this question is the absolute minimum occurs at x equals -1, and the value is, so at the point, -1, -3 on the function. And the absolute maximum occurs at the point x equals -0.115, and y is 2.059. That is the answer. Now, a lot of times students skip the endpoints and just give me the local max and local min. You have to check the endpoints if you're asked about absolute minimum and absolute maximum. It's that one more step you have to do. So we're going to move on to a word problem example in a moment. And in our word problem, we are doing a nice spring activity of laying out a garden. So you're going to lay out a garden, and you're going to make it in a rectangular area. You're going to protect it by a chicken wire fence to make sure little animals don't come in and eat your garden. Doesn't always work, but you can try. So let's draw a rectangle. It's the first thing. It tells me I'm dealing with a rectangle. Let's draw a rectangle. There's a rectangle. I want to find the largest area. So what I'm maximizing is the area that can be protected with 100 feet of fence. Well, what that means is as I go around and add up how much fence is on each side, it has to add up to 100. So I've got a length and a width. I don't know, we'll call this L and we'll call this W. And then there's a W over here if it's a rectangle and an L. And L and W could be the same value if that rectangle happened to be a square. But we don't know that to begin with. But what I do know is the perimeter is the amount of fence I need. And the perimeter of this will be 2L plus 2W. And my problem tells me that at most, I only have 100 feet of fence available to me. So that 2L plus 2W has to equal 100. I'm being asked to find the largest area. Well, that's different than perimeter. The area of a rectangle is length times width. There's two variables there. I'd like to turn that into an equation with one variable. So this is what I need to maximize, is this area equation. Right now, it's in two variables, but what the perimeter information over here does is it allows me to express one variable in terms of the other. I'm going to solve this for W. And then I divide both sides by 2. And I get W equals, I can do 100 divided by 2 and 2L divided by 2. I do get 50 minus L. Be careful. I can only do that because I'm dividing both of these things. If it was 100 minus L over 2, I could write 50 minus L over 2, but not just 50 minus L. This is proper for this example, though. So I find an expression for W, and then it's kind of the two equations to unknowns method of substitution. You replace that W with 50 minus L. So my area is going to be L times 50 minus L. I want to maximize that. Now I could use the product rule, but it'd be easier if I just expanded this to say 50L minus L squared. Because to maximize the area, I want to find the critical values. I want to find the derivative of the area and where that derivative is equal to 0 or undefined. It's defined everywhere for L. Up to L is 100 feet. The most L could be is 100. Actually, the most L could be is 50 if there's two of them, but then you have 0 area. If L was 50 and this L was 50, there's no width. You just laid the two pieces of fence next to each other. But here, I'm going to look for the critical values to see if there's some value in between 0 and 50 that will work. So I find out where this derivative is equal to 0. And I add 2L to both sides. And I get L equals 25. So when L is 25, well, I can also do some analysis based on what I know about quadratics here. This is a quadratic. It has a negative value in front of the squared term, so I know the shape of that quadratic is going to be like that. So this 25 is going to be a maximum. But I can check. I could check. I could put in L is 24 here, and I would find out that my function was increasing. My slope was positive. This would be the sine of A prime. And then I could see that my slope here was negative. Or I could take the second derivative. And to do that, I would find A double prime equals negative 2L. I'm sorry, not negative 2L, negative 2. A double prime is negative 2. Let me start that over. A double prime, let me erase that. If I found the second derivative, there's my first derivative. The derivative of 50 is 0. The derivative of negative 2L is negative 2. That is always negative, which means this function is concave down, which means you have a top, not a bottom. You're at a top. The concave down looks like this, so you're at a top. So that's definitely a max. And as I said before, the endpoints of either if L is 0, W is 50. And if W is 0, if L is 100, W is 0. Those are minimums. You get an area of 0. So you don't need to consider the n so much there. And what I get is L is 25. But if L is 25, What am I asked for? Give the dimension. So I want length and width. I go back here for my width. Width is 50 minus 25. So I get a 25 by 25. I get a square, would be the optimal area. Okay, so that is an example of a word problem where you need to use optimization, you need to use the critical values, and you need to consider endpoints, although then it's kind of open-ended for this one. That's all I have for this video. In the second video that is posted, you will see an example of minimizing the amount of material used in the can to make a certain size of a certain volume can. And please email me your questions.